Hey, welcome back, chemists. Great to see you. Today we're going to be studying vapor pressure and boiling point. Now you might be thinking, what does that have to do with solutions? I thought we were studying solutions. Well, next class we're going to be studying how are these properties different for solutions when you add a solute. So we're going to start with just the concept this week and then add on to it with solutions next time. So today's aim is 8.7, what determines the boiling point of a liquid? And I'm going to go through the question of the day, sort of walk you through what the demo would have been if we were in class. And then the lesson is on vapor pressure and boiling point. And then we're going to start homework 16 with any extra time. All right, so question of the day. We've got a saline solution at the grocery store. You find on the shelf there, it's 100 milliliters. And it says it's 0.1 molar sodium chloride aqueous. So the question is to describe the steps you think the chemist undertook to make this solution. How much of what did he or she add to what? All right, well, we can tell that there are 100 milliliters of water, obviously involved. We can tell that's one ingredient. The other ingredient appears to be sodium chloride. So we know we need 100 milliliters water. We could measure that out pretty easily with a graduated cylinder. But how do we make it 0.1 molar sodium chloride? So let's see if we can figure out how many moles that is. So I'm going to remember my molarity equation. Molarity equals moles per liter, or if you like the magic triangle, molarity is moles per liter. There we go. So we know the molarity, we know the liters. We're trying to solve for moles. So the molarity here is 0.1. Milliliters is 100. So if we want to change that to liters, to go from milli to liters, we move the decimal over 3 places. 1, 2, 3 to the left. So it's 0.1 liters. So 0.1 liters, 0.1 liter times 0.1 molar. And that equals 0.01 moles. So the chemist just got 100 milliliters of water and 0.01 moles of sodium chloride. Now, we don't usually just grab moles of things, right? What's an easier way for us to measure out that amount? Grams, of course. So we'll just want to change the moles into grams to figure out how much to weigh out of the salt. So if you don't happen to have your reference tables handy, here's the mass for sodium and chlorine. So looks like 23-ish, 35.5, so 23 plus 35.5 will be the gram for mole mass of sodium chloride. So that's 58.5 grams per mole. So I'll just take my moles here, 0.01. And if you have a unit that has to go, where do you put that unit? Down below. And if you have a unit that you love, put that unit up above. 58.5 grams per mole. You probably do that math in your head. That's 0.59 grams of sodium chloride and 100 milliliters of water. Stir it together, you've got your saline solution. So hey, now maybe you don't have to buy it at the store, you can make it yourself. All right, so let's take a look back at homework 15. These were all the percent by mass, percent by volume, and parts per million equations. And remember, those are all on the back of your reference tables. under the concentration there with next to the molarity equations. So you can find all of those on your reference tables. And you can take a look through here at your leisure, take a look at my work and see what questions you have. One thing to note is sometimes it's easy to forget about the solution mass being in the denominator as opposed to just the solvent. You want the whole solution's mass down there. So that will be the solvent plus the solute. So that'll change your numbers. Also in a couple of them, you're also using reference table G. Like in number 6, it said, what is the percent by mass of a saturated solution of potassium chloride at 20 degrees Celsius? So I looked back at table G to see how many grams of solute are in a saturated solution of potassium chloride at that temperature. So here's 20 degrees Celsius, here's KClO3, potassium chloride. Here's the line there. Looks like about 8 grams of solute would make it saturated at that temperature. And then this is in 100 grams of water. So 8 grams out of 100 plus 8 grams times 100% is 7.4%. This last one was kind of interesting because you're looking at the same solution in 3 different ways. The concentration in parts per million, the concentration in percent by mass, and then the concentration in molarity. All right, so let's get to the demo that we would have done if we were in class. It's a pretty simple one where we're just boiling water in a flask, but we're thinking about some of these questions. The first one is, how can you tell when something is boiling? Bubbles, right? Okay, so what is a bubble? Some people say it's full of air. By that, do they mean oxygen? If so, that's not true. The bubble is not made of oxygen. That's right, it's made of water vapor. It's water in the gaseous state. That's what the bubble is. It's water that has so much energy it's turned into a gas. And now all those particles are in a spherical shape and they are less dense, so they're rising to the top of the liquid. Okay. Now we're thinking about, why do those bubbles not just crush back into liquid? They've got all this weight of the water on them, right? Well, it's because they have enough energy to be able to push out against their own intermolecular forces and each other. And that's how they're able to form a bubble. So what would happen if the air above them had fewer molecules in it? Now you can imagine the weight of all that air pushing on top of the liquid is less. So then the water would need less energy to make a bubble. The last part of this demo is where I put a balloon over the flask, and I'm sure you can imagine what happens. Yeah, it fills up with water vapor, hot water vapor, and sometimes it shoots off and hopefully doesn't hit anyone. Yeah, and then the balloon is full of water as the steam cools back down and turns into a liquid. Cool. All right, so that's going to be what we're talking about today as we look at 8.7, what determines the boiling point of a liquid. Question, do you think it's easier or harder to boil water at high elevation? All right, we'll come back to that question at the end of the lesson, but keep your thoughts in mind. Do you think it's easier or harder to boil water at higher elevations? All right. This picture shows 2 flasks of 2 different liquids, and we're wondering which one has a higher vapor pressure. You might be thinking, what is vapor pressure? Well, vapor is just another word for gas. It's just a word we use for gases that we're used to thinking of in their liquid form. For instance, people don't usually call it water gas. They call it water vapor because we're used to water being a liquid. So which one has more little particles of gas exerting a pressure? Well, the one on the right, right? Vapor pressure is just a force exerted by gas particles. So that would be this guy. It has more gas particles there, so it has higher vapor pressure. It's exerting more pressure from its gaseous particles. All right, so now let's imagine which of these has higher vapor pressure. All right, well, substances that have very high vapor pressure, or in other words, that evaporate really readily, we call those substances volatile. Like gasoline is pretty volatile. That's why it's kept under pressure in the gas station. They don't just have buckets of it out that you can scoop up, right? It's very volatile. Motor oil, on the other hand, you can just buy at the store in a container and pour it into your engine because it's non-volatile. Non-volatile are liquids that do not evaporate very readily, or in other words, they have generally low vapor pressure. Okay, so which of these do you think is more volatile? Hot water or cold water? That's right, hot water. It's really ready to evaporate if it's already hot, right? Some of the particles already have evaporated. So there's lots more gas particles in the air of the hot water. All right, which of these do you think is more volatile based on your life experience? Water or alcohol? Some of you know that one of these smells more than the other one. That's a sign that it's volatile, because that means particles are evaporating and getting in your nose. Yes. So if the rubbing alcohol is more volatile than the water, which do you think has stronger intermolecular forces? Because we're imagining they're just at the same temperature, both just sitting there, but the alcohol is evaporating and the water's mostly just staying there. So which has stronger intermolecular forces? Yes, it must be the water. Those stronger intermolecular forces are holding it together, keeping it from evaporating. Alcohol must have weaker intermolecular forces, so it's a little easier for the particles to have enough energy to evaporate. So that gives us this other relationship. The stronger the intermolecular forces, the higher the boiling point. And in fact, boiling point is the best way to measure how strong an intermolecular force is, because anytime you're boiling something, you're not breaking bonds. It's not like you're taking H2O and breaking apart H's from O's. You're breaking intermolecular forces. You're breaking apart an H2O molecule from another H2O molecule, held together with strong intermolecular forces. So the stronger those intermolecular forces are, the harder it is to boil something, therefore the higher the boiling point. You can picture the little magnets that we used in class, those models. Okay. So this brings us to our next reference table. Reference table H is the vapor pressure of 4 liquids. There's not a ton of natural liquids that you find on Earth, mostly just water, but here's a few. And so we can compare their vapor pressure over temperature. So take a look at the graph and notice what happens to vapor pressure as temperature increases for all 4 of them. Does it increase or decrease? That's right, it increases. And you can imagine why. As temperature increases, vapor pressure increases, because as temperature increases, the more those particles have energy and the more kinetic energy they have, the more likely they are to break past their intermolecular forces, boil, turn into a gas, and exert vapor pressure. So as temperature increases, vapor pressure increases. Oh, and this is on page 4 of your reference tables if you have them. So let's go back a moment to this point, and then we're going to come back to table H again, thinking about what is it that makes water boil. So for those bubbles to form, for them to be able to have enough strength to exist, the vapor pressure has to be at least as strong as the atmospheric pressure pushing down on them. The bubbles have to be at least as strong as the air. right? So that the bubbles can form and they don't just collapse. So that means boiling point is the temperature at which vapor pressure is at least as strong as atmospheric pressure, or it's the temperature right there. We know that vapor pressure increases as temperature increases. It's the temperature at which vapor pressure equals atmospheric pressure. Cool. So then those bubbles can form and rise since the vapor pressure can overcome the atmospheric pressure pressing down on it. Right? And just a reminder that regular atmospheric pressure, like in this room right now, probably the pressure is about 1 atmosphere. And when we talk about STP, standard temperature and pressure, standard pressure is 1 atmosphere. There's a lot of ways to measure pressure. So if you're measuring in kilopascals, that's 101.3 kilopascals. And those are on the front of your reference table. Okay. So knowing that, what would be the vapor pressure if something is boiling? Well, we know the vapor pressure has to be as strong as the atmospheric pressure, and the atmospheric pressure is usually 1 atmosphere. So that means the vapor pressure at any liquid standing boiling point is about 1 atmosphere. All right, so let's take a look now back at the vapor pressure for liquids table. And we can see that dashed line, 101.3 kilopascals, that represents normal air pressure. So where that dashed line intersects with each of these lines, that must be the boiling point. So for each substance, we can just look down at the x-axis to see what temperature they boil at. So propanone boils at 55 degrees Celsius at normal atmospheric pressure. Ethanol, you'd usually have to heat up to 80 degrees Celsius. You know what temperature water boils at? 100 degrees Celsius. And then ethanoic acid is even harder to boil. You have to heat it up to about 117 degrees Celsius. So which one of these requires the most heat to boil at standard pressure? Yeah, ethanoic acid. So which one do you think has the strongest intermolecular forces? Right, probably ethanoic acid, right? Yeah, gotta be. Okay, so let's think back to this question I asked at the beginning of class. Do you think it's easier or harder to boil water at high elevation? Got your answer? All right, here's the boiling point in Fahrenheit at different elevations. So down at sea level, if you're in downtown Portland, you'd have to heat the water up to 212 degrees Fahrenheit for it to boil. But if you were up on top of Mount Hood, you'd only have to heat the water up to 194 degrees Fahrenheit. So it's a little easier to boil water at high elevation. How come? Well, the air is thinner. It exerts less pressure. So if we look back at this table, instead of atmospheric pressure being up here, the pressure would be down here somewhere. And if there's less pressure, then there's less pressure the bubbles have to overcome. So you don't have to heat them up as much in order to boil the water. All right, so let's take a look at some examples. Example 1, the vapor pressure of ethanol at its normal boiling point would be, let's look at our table H here. Here's ethanol, and it asks for the vapor pressure. It would be 101.3 kilopascals. And that's true for any substance that the pressure at its normal boiling point is atmospheric pressure, 1 atmosphere. All right, example 2. If the pressure on the surface of a sample of ethanoic acid is 40 kilopascals, then it will boil at, let's look at our graph. So here's ethanoic acid. Here's 40 kilopascals. Looks like the temperature would be about 90 degrees Celsius. All right, that's it for this lesson, you guys. You can get started at homework 16. I do have one summary question for you, and you can pause and do the homework first and come back to this, or you can look at it right now. Which of these liquids generally has the highest vapor pressure? We've got propanone, which is nail polish remover, acetone, ethanol, which is fuel. Oops, that should say fuel, not fueled. And ethanoic acid, which is another word for acetic acid, which is also known as vinegar. So which of these has the highest vapor pressure and which has the strongest intermolecular forces? So highest vapor pressure, let's just look at regular room temperature. Looks like the one that has the most vapor pressure at that temperature and at any temperature is propanone, highest vapor pressure. All right, which has the strongest intermolecular forces? Well, that's going to be the one that's hardest to boil or with the lowest vapor pressure. So ethanoic acid. Awesome. Thank you guys so much. And let me know if you have any questions. Bye.